So unfortunately, that's all the time we have. So we'll be moving to the next speaker, which will be Nicolas Guignot, so from the SOLEIL synchrotron, and he'll be talking about the PSICHE beamline, and more specifically, how to use it to study, of course, the Earth and planetary materials.
Okay, so thank you for inviting me today to give this presentation about the new techniques we developed over the years at SOLEIL on the PSICHE beamline. So the PSICHE beamline is mainly dedicated to high pressure science, X-ray diffraction and imaging. And we have a large range of tools, a large volume press, diamond anvil cell, and techniques to access the pressure and temperature range of the deep Earth and to measure the physical properties of geomaterials in such conditions. The PSICHE beamline is a Wiggler beamline, so that means that we have lots of flexibility on the beam. We have two hatches. In blue, you have the monochromatic beam hatch dedicated to laser heated diamond anvil cell and tomography. But today I will focus on this hatch, the white beam hatch, that is dedicated to large volume press experiments and high-speed tomography. Okay, so in this white beam hatch, the beamline configuration is straightforward. We have a vertical focusing mirror that we can use to focus the beam in the vertical direction. The attenuated white beam, so now the pink beam, can be used for imaging applications, and the white beam is used in energy dispersive configuration for X-ray diffraction. So this is a very specific energy dispersive method that I'm going to present now. So the first technique I would like to present is the CISAR X-ray diffraction technique. CISAR stands for Combined Angle and Energy Dispersive Structural Analysis and Refinement. It has been introduced by Yan-Benny Wang and collaborators in 2004. So basically, it's combining energy dispersive and angular dispersive X-ray diffraction. The detector is mounted on this rotation axis, and the slits in front of the detector are always aligned with the sample, whatever the angle, at all angles. And this is a very convenient and extremely interesting technique when it's paired with large volume presses, and specifically the multi-angle press. It's designed to produce reliable structural information thanks to the combination of EADX and ATX. There's a very effective background removal and intensity correction, intensity of the peaks. It's designed for data acquisition in large volume presses, as I said, because of the limited aperture of the presses, this can be a problem. There's suppression of undesired signal, the sample environment of the sample. So this acts basically like a solar slits system, but adapted to very large equipments, like the multi-angle press. And if we need, we can just fix the angle of the CISAR system and then collect data at this fixed angle. This is the standard EDX system. And we can do very fast acquisition in this configuration, down to 100 milliseconds or even less. So that's the ideal tool for the study of liquids in large volume presses. This is a picture of the setup on the beamline with the slit system, with the micro slits, and the germanium detector we use. It's 7 elements that are behind the slits, and the accretion axis. This is the press we use with the CISAR system. So this is the multi-angle press. It's a 1200 tons capacity, 2400 degrees total aperture. We have a dia module, and it's compact and light, and it's not permanent on the beamline. So we needed to remove it. So it's removable and placed only for the proposals that need the multi-angle press. This is a typical diagram, Caesar diagram, with on the horizontal axis you have the energy, on the vertical axis the angle, and you can see on each line a diffraction, an energy dispersive X-ray diffraction. From this data set, it's possible to remove the background and to correct for the intensities to get this I of Q. Here it's measurements done on liquid iron sulfide, measurements done by Xu and collaborators, published this year. And you can see the first two bumps of the liquid on the diagram and on the I of Q. And finally, from this I of Q, it's possible to get the G of R and F of R, from which the density can be calculated thanks to the linear fits below R0 following the method developed by Egert and published in 2002. So Xu and collaborators did these measurements for different sulfur contents and also at different temperatures. So you have all the I of Qs. And from this data, they could get the G of R, F of R, and get the densities. And here you have the temperature dependence, so thermal expansion of the liquid. Iron sulfide alloys at constant pressure here at 7 GPa for different sulfur contents. So this has implications for the solidification regime of iron sulfide cores, restorids, and small planetesimals. The next technique I would like to show today is the UTOPEC. So it's a new VX type PE Paris-Andrews cell optimized for high-speed tomography. It features a panoramic design, 165 degrees. It's compact. We have included rotary joints for resistive heating. We can put up to 300 amps and water cooling. It fits our high precision tomograph. You can see it. You can see it moving here on this movie. It's used in pink beam mode for better contrast, less beam hardening, and high flux. So thanks to the beam flux and the macro tomograph, we can produce up to two tomographs per second at high pressure and high temperature. The pressure and temperature ranges that we can achieve is the typical Paris-Andrews cell pressure and temperature ranges. The spatial resolution is about 5 microns with the field of view of 2.8 by 2.8 millimeters. So it fits perfectly the sizes of typical large volume loadings. Possible applications are time-resolved experiments and snapshots of sample volumes at high temperature. One of the first applications of this technique was this paper by Boulard and collaborators published last year, following the phase transitions of iron in 3D with X-ray tomography and diffraction at high pressure and high temperature. I'm just showing the transition from alpha to epsilon iron. On the left, you see from the starting sample was a single crystal of iron. And you see here that the epsilon iron platelets growing with time during the transition. But there's more when they combine X-ray diffraction and also Fourier analysis of the 3D reconstructions. We managed to index the orientations of every platelets inside the reconstruction. The next application is a paper that has just been published last week by Jovenko and collaborators about the migration of carbonates, liquid carbonates inside the silicate matrix. Here on the top, you have an example of a segmented carbonate blobs from a 3D reconstruction obtained after a tomography of 1 second. And here you have the evolution of this melting prolongation with time. So each frame here, you have on the bottom of each frame is the location of the original carbonate layer. and the height of each frame is the silicate matrix. So it's lateral projection here, you can see. So it reads like this from top to bottom. And what we see and what the authors saw in this paper is that with time, melt blobs are more numerous and located further from the initial layer. And once porosity is filled, the elongation, flatness, and depth of the associated pockets remain relatively constant over time as its volume grows. Next, this is not tomography, but still high-speed imaging. So here I'm talking about high-speed radiography that is adapted to the multi-enterprise. In this case, this is viscosity measurements done at high pressure and high temperature using the 4-sphere method. Here, the authors, she and collaborators, managed to do these measurements at very high conditions, like extreme conditions for this type of measurements. Here, I'm showing the force-to-rate composition, 24 GPa, 2500 degrees C, recorded at 1000 frames per second, thanks to the high flux of the ping beam. And the terminal velocity of the sphere is used to get the viscosity of the melt. And this has very interesting implications for the crystallization regime of the magma ocean. Last technique I would like to show you today is the Berlambert absorption method to measure the density of liquids. So this method is not new. Actually, it's available in many synchrotrons. It's very straightforward. What you need to do is just to scan the sample in front of a monochromatic beam to get the absorption profile. And then you use the Berlambert law to get the density of the liquid. With the Berlambert law, you have the density, you have absorption coefficient, and thickness of the sample. So the density is what we measure. The absorption coefficient is known at a given energy. This is why we use a monochromatic beam. And the thickness is fixed because loadings are done in diamond capsules. But as you remember, this beamline on research, we don't use the monochromatic beam. We use the white beam or ping beam. And we want to keep this white beam and ping beam to keep the techniques I've just presented before, the high-speed tomography and the CSR X-ray diffraction technique. So we had to find another way to do these kind of measurements. And the idea here is to change the configuration and put the polychromator after the sample, keep the white beam, and change the slits of the CSR diffraction system to get the diffraction pattern of the polychromator. Here, the polychromator is very simple. It's just a pellet of an MgO powder, so very, very simple object. So now the CSR system records the diffraction patterns of the polychromator, no more the sample. And then the density measurements can be done by monitoring the intensities of selected diffraction peaks of that polychromator as a function of the position of the sample using the Berlambert law as normal, just like the monochromatic beam configuration. So this is an example done by Laurent Henry, my postdoc, a density measurement of liquid gallium at high pressure. If we put the detector angle at 8 degrees, we have two diffraction lines, very strong lines that we can record. The first one at 38 keV, and you have on the left the evolution of the intensity of that diffraction peak and the corresponding absorption profile on the right, and another line at 54 keV and the corresponding absorption profile. And you can see that we have two benefits, interesting benefits here. It's possible to tune the detector angle to select the energy, and it's very easy. We can go from 15 to more than 100 keV in a few minutes. Just have to turn the detector. And we have simultaneous measurements of the density at different energies, which is also quite unique. Here I'm going to have a look to a specific example. If we look at this fit, we see that the fit is not very good because the fit in red considers that the sample is perfectly is a perfect cylinder. But when you look at the high-speed tomography that we could do at the same time, you can see that there are bubbles inside the sample. Here, you see the strength of combining high-speed tomography with the absorption measurements, because now from this 3D reconstruction, it's possible to determine the exact geometry of the sample at the position of the measurement, the absorption measurement, and produce another fit like so. So here, I'm considering not a perfect cylinder, but I'm considering the real geometry measured thanks to high-speed tomography. And this is, to me, this is very interesting, because that means that we don't need anymore to consider a perfect cylinder. Maybe we don't even need anymore to have diamond capsules to make these kind of measurements, since we know exactly what is the geometry of the sample, position of the measurement. Another benefit is the multi-technical approach to the study of MERS. Laura did the measurements of the measurements of the density of the gallium using the Berlambert law I just mentioned, but also done the measurements using the X-ray diffraction from the CESAR, so using the Egert formalism that I presented earlier, so completely independent measurements. And another independent measurement is the measurement of the full volume of the sample using tomography, high-speed tomography. So 3 totally independent measurements of the density, and you see that the data is pretty consistent. So in conclusion, PSICHE provides some unique tools, CESAR, U2PEG, Berlambert absorption measurements in white beam mode, specifically designed for high pressure science using large volume presses. We have a multi-technical approach ideally suited to the study of liquids, structure, density, thermal expansion, mobility, viscosity. We have much more. I cannot present everything, but we have also implemented the ROTOPEC, which is another device for tomography, not high speed this time, but very strong, very nice tool to get the deformation and X-ray completed tomography. We have also laser heated diamond cell, and we have developed the 4-color chrometry for this setup and other stuff. Thank you. I would like also to thank all the users for their input that made all this development possible. Thanks.
Thank you very much, Nicolas. Do we have any questions for Nicolas? I don't see any hands raised, so maybe I'll sneak in one of mine. So you showed us 3 different techniques that could measure density. Which one would you say that is the most accurate? And do you need to always measure to always use more than one in order to get correct measurements? What would you recommend?
Well, for density measurements of liquids, I would recommend the Berlambert absorption method. It is the most straightforward measurements, but there are some difficulties sometimes. But I think this is the best, because with X-ray diffractions depends on the material. It can be difficult to get the density from the diffraction, and getting the full volume of the sample can be also difficult, because sometimes the anvil gap is just not high enough, big enough to get the full volume in tomography, high-speed tomography. So density measurement, that's why we developed this technique. Actually, our users base, they wanted a lot this technique, because they see the strength of this technique. This is why we developed it. But again, I think it's the combination of every technique that is very interesting.
Yeah, you showed us a combination of Berlambert and then the high-speed tomography to get more accurate.
Yeah, I think this is very powerful.
Yeah, quite neat. Okay, for those who might have other questions, please don't hesitate to type them in the chat, and Nicolas will make sure to answer them. With this, I thank you, Nicolas, for your nice talk.